Started and continue on. As you know, we've been working with Faraday's law here in chapter 31. It's one principle, which sounds simple, but as you saw with some of the calculations we did, can get a little tricky looking at all the calculus that's involved. We've got an integral of area, we've got a derivative of time, and the other side of the equation has a line integral. So if you put all that together, then it's one simple equation. That's it. So let me show you the rest of chapter 31, which really is no new physics, just one more example. Then we'll do concrete examples, if you will, from the back of the book, and just do as many as we can. And if time allows, which I hope it does, we'll actually start the next chapter there in 32. If not, well, then that's what we'll pick up after we come back. Pardon me? Oh no, because of the Thanksgiving, yeah, there's no lab. There's no lab on Thursday. I was thinking because that lab was missing, to make it fair, you should have the Wednesday do too, right?
Yeah, I was thinking
But we'll just won't do one on Wednesday afternoon or on Thursday. Yeah. So that's the schedule.
So we're not having one on Wednesday?
No. So there's not one on Wednesday if you looked. Yeah. And that's not a change, but maybe it should be pointed out. If you look in there at the syllabus, you'll see that this week where it says Thanksgiving, yeah, it says holiday just across the board. So, but it's Wednesday too.
Okay.
Right.
Can you talk to Dr. Nick and get him to cancel the quiz on Wednesday afternoon?
Oh, that's your job. Well, did you say you were going somewhere?
7 hours north. Yeah.
Oh, in traffic.
In traffic, yeah. And we used to expect us to show up to class.
All right.
Maybe like 4 in the morning.
Well, the very last thing I want to show you, and maybe I should put it on the board, but I don't know if I'd say this is the most important of the applications, but certainly one of the dominant ideas of this chapter. I'll put Faraday's law on the board here to begin with, but I think I got this across fairly well, and that's this point here, that an EMF, which of course we could change that into a line integral and call it an electric field. We did a few of those, okay? But an EMF or an electric field, however you want to look at it, is created when there is a change in the magnetic flux. Maybe a change in the field strength because the magnet got closer and further, the wire got closer and further, the current that created the magnetic field changes, or in this case, one of the simplest one is this picture here. These are generators. This will help answer an important question that we've kind of said along the way, but are really going to dive into deeply after the Thanksgiving break is, then what is the EMF or what is the voltage in these wall plugs? All right, it has a certain voltage, which we'll talk about that in more detail later on, not so much here in this chapter. But the most important thing I want you to see in this chapter is it has then a frequency. It has an altering current, an AC. And so look at this little device. Let's go through a couple of steps here. This is a generator. Here is my little model of a generator. Maybe I will actually disassemble this one and make it look like that one here. But here is the loop. Here are the contact points, but if I were to set this in something like that, and maybe I'll hold it this way so you can kind of see it spin, but if there's some magnets on each side, which again in this one they show a north pole and a south pole, as this thing is spinning around, isn't the flux through this area changing? In other words, when we're at this position, how much flux goes through that loop? Well, there's north. Which side's north? North. And so the magnetic field goes that way. And when the plane is parallel to it, that is the normal vector is perpendicular, no flux is going through, right? And so as it rotates, more flux, more flux, more flux, more flux, more flux, more flux, until we get to a maximum amount. And then less, 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 less. to 0 again. Then more, or what you might say more in a negative direction, till we get to a maximum negative. Can you say that? Maximum negative? Don't tell your math teacher, but okay. So there's minimum, how's that? Maximum negative. And then less, 0. Okay? But the point is, if this thing just sat there and spun, as it is spinning around, isn't it always changing flux? And in one part of the revolution, the flux is increasing, and in the other part of the rotation, it is decreasing. And so that is why you would get an alternating current. In fact, you saw me do this once before. It's probably worth seeing again here. But if I take then a large coil and a magnet that is spinning, and so either the loop spins or the magnet spins, and in this case it's easier to just have the magnet spin. But as the flux goes one way then the other way, you can see with the ammeter I create a current that goes one way, then another way, one way, and then another way. And so there is a change in flux. And that's why our wall plugs are, and not the only reason, but a good reason is that it makes an easy way of making an AC circuit. You just spin this. And some of you, I think, even know the rate. What is the rate that this thing spins? Okay, 60 hertz, 60 times a second, or 3,600 RPMs, right? And so that's the rate at which our generators are designed for our grid. If I go through some math here, look what comes out of this. I'll say, all right, if I take a loop, let's start with N, just as to recap. What is N in that equation? Okay, so it's the number of loops where? Okay, in this coil. This case, it would be 3,400. This picture kind of looks like it's 1. I'm sure a real generator has some number N, so I'm just going to leave it as an N. Okay, keep that in mind. Then I have the derivative of the flux. And here's where you hopefully see in the math, why does the flux change? Well, they're trying to design a field here with these bar magnets that is uniform. So it's not the field that changes. What changes? Which? It's theta, right? It's not the area of the loop. It's not the magnetic field. It is the angle. And so that's what happens as this thing spins. So as I simplify this a little bit, I'll leave the N alone. I will take the point of view that the B is a constant. And maybe I should pause right there. And even ask, B is a constant over space. Is it a constant with time? Okay, yeah, in this case it is, because I am just creating a magnetic field from some permanent magnet. So I would say right here, this is a permanent magnet. B doesn't change. So even though I only pulled it out in front of the integral of area, I could have pulled it a little bit further, and I will now. I will pull it in front of the time derivative. Let's start with the next part. What about the angle? Is it a constant? So can I pull it out in front of the integral? Okay, so it's a constant with space, but changes with time. Now let's look closely at this, right? So if I pull one of these up here at an angle, if it is at some angle like this, every little piece of area is in the same direction as every other piece at that moment in time. And so, at some moment in time, if I were to add up over the area all the little dAs that make up the area of that loop, I would say, yes, the angle is a constant in space. I'm going to put it here. maybe I should have left this in here for a second. And so I'm going to argue that I can pull the cosine of the angle in front of the space integral. But as you just said, can I pull it in front of the time derivative? No, because that's the moving part. So that's the part that gives us the change in the flux. And so then I've got this dA. In fact, a couple more steps here then. This EMF is negative NB. So there's the NB. And when I do this integral for the area, that's A, I'm going to claim that that does not change with time. And so I got an A here, but I'm going to pull it all the way in front of the derivative, because again, as this thing spins around, you can kind of see this loop. Does the area of this loop change? No. It's again, what's changing is the angle. So that's how these generators, kind of simple, are designed. They change the flux by changing the area. You just spin them around in a circle. So the final step, or maybe two more steps here, is I've got an N, a B, an A. What's the derivative of cosine? Okay, negative sign, so I'll change that one out. That becomes sine theta. What else? Is there a difference between these two? Right? This is the derivative with respect to theta, and then that, well, maybe I should have done cosine. Cosine, cosine. Yes, this becomes a negative sign, but this, right, as a chain rule, right? So I have a d theta dt. And what would you call d theta dt? Yeah, going back to our rotational mechanics of Physics 121, this is then the angular speed. This is that 3,600 RPMs, the 60 hertz. So this is the omega sine theta. And if you wanted to write it as a function of time, maybe you could even also add to our mechanics that the angle would be omega t. And so just like distance equals to velocity times time for a constant velocity, angle equals to omega t for a constant angular velocity. So there would be the EMF of our generator. And that was the final example that your author did in the chapter by saying, look, take something as simple as this, a single loop in a constant field. As you spin it, what are you going to get? You're going to get an EMF. But look closely at that EMF. That EMF, as a function of time, changes, right? It has this as its amplitude, and it keeps getting bigger, smaller, bigger, smaller, bigger, smaller. And so that's how to generate an AC voltage, really simply. And so that's our wall plugs, and that's what we're going to be spending, like I said, a lot more time on in these last couple of chapters, is understanding the grid and the fact that it's 60 cycles or whatever. So this is going to come up to an N, a B, an A times omega. And those of you who might know more about the grid will see this in the next chapter. This is about 170 volts. And so our little grid is designed to go up to 170, go down, and go down to a negative 170. And so it goes up and down and up and down and up and down. More on that later, but there is our generators. If I kind of show a few generators besides this one's nice to see, but I like this one in particular because most of you will recall seeing this one already. You saw it as a motor. And so what I did before was to take and pass electricity. I hooked this to a power supply, remember? And I sent electricity through here. And as I sent electricity through here, it made it move. But the reverse is also true. What if instead of sending electricity through it to make it move, what if I make it move? It will make electricity. So the generator and the motor are essentially the same physics, just one is running what I would call forward and one in reverse. And I guess we could define which one's forward and which one's reverse. But since we saw the motor first, I would call the motor forward and I would call the generator reverse. But if I hook this up and spin it, spin it. Oh, maybe I got to get it. See, nothing. Oh. No? Yeah. Oh, there was a little movement. Maybe I just didn't have enough spin. Not much. I swear we got more on this in the past. Maybe I don't have a good connection here. Oh, that does look pretty sad. Maybe I can scrape it clean a little bit. Oh, so does that. All right. Hey, I'm going to go with that's what's wrong with it. But
will the coil serve as an inductor?
Ah, there it goes. Usually does a little better than that, but maybe that's the best I'm going to show you right now. Yeah?
Will the coil serve as an inductor that absorbs the first moment of current?
Yes. Yes.
Longer, it has to produce more. The current will go up.
Oh, yeah. And, well, and it sounds like you guys already talked about it in your circuit, but that's exactly the next chapter. That's why I'd like to kind of see the next chapter before we're done with today. But not sure we're going to. Well, I brought some better ones. That's obviously got a little troubles there with our context, so I'm going to have Dawn clean that one up. But I really like this one just to kind of illustrate. Unfortunately, it works great. But unfortunately, you can't see the moving parts. But here's the handle. And inside here is a gearing system and a nice magnet that spins around. Kind of like those flashlights I passed around last time. Because if I were to hook this up, I'll just maybe put it something like this. And from your position, maybe you can see that I have this generator then hooked to a little circuit here that happens to be a light bulb. And so maybe if I set it here and crank the handle, you can see the electricity that's generated. If I close that switch, well then that light bulb and that light bulb are now in parallel. And so again, I can generate the electricity. What's kind of fun is to turn on both lights, or just one light, or no light. And you'll feel that on your hand as you turn it around, because obviously in this case, you are just generating a voltage without any current. Here, you're generating a little bit of current. Here, you're generating a lot of current. And then, if you remember the problem we did and the one we're about to do, if you generate a current and then the current is flowing in here, and so this thing is spinning around with current flowing in it, then there'll be a magnetic force on that wire, and it'll be like the motor. You will feel the strain in your hand depending on how many lights you are turning on. And so that's why it's kind of fun to pass this one around. And I will, except I will add to it this one. Here's the second one. And the point here of the second one is, again, to show you that the generator or the motor are really one and the same. That is, if I hook these two together and I crank this handle, then this one is the motor. if I switch it around, then that one's the motor. And so the motor and the generator are the same physics, just one is operating what I would say forward, and one is operating what I would say reverse. And so they're kind of a nice little setup with all that.
So if nothing's connected, where does the work go?
Well, I'm doing very little work. You'll feel that in your hand because none of my work is going to electricity. All it is going into the friction of those gears as I turn them around. But as soon as I make a connection, then you'll feel that in your hand where the work goes. Oh yeah. Oh, hands down. No doubt about it. In fact, these are common if you ever get to some science museums and stuff. Usually, they usually have them. I know the one down here in LA. This summer I was up in San Francisco. They had a great one. And in that one, they had it hooked up so that you could push with your legs, so you get a lot more. And then they had a series of lights, and you can turn them on and off. And you turn one light on and pedal, not too bad. You turn 2 on, not bad. 3 was really hard. Oh, it is a tandem, so you can put a second person in there, and the 2 of you can turn on the 3 lights, the 4 lights, and so. Yeah, but you'll definitely feel the difference in load because you're doing different amount of work depending on how much current you're generating based on how many lights you're lighting up. Yeah. Well, that's the last step here in the chapter. So let me try some example problems. That's really my goal here for today. I've got number 9 on the list first here, and so as a good first example here, let's try number 9. Problem 4, 8, how come there's 9, hiding over there. All right, I didn't see it there. All right, so here's the problem, or here's the picture in it, and it says the following. Pass some current through, and I just want to read it here. What chapter is this, 31? It says here, an aluminum ring of radius 5 centimeters and of resistance 3 times 10 to the minus 4 ohms is placed around one end of a long air core solenoid with 1,000 turns per meter and a radius of 3 centimeters as shown in the figure. All right, so here's the figure, here's the picture. You have the solenoid here which has current going into it. They give you the radius of it. You have a bigger ring which is made out of aluminum. Hopefully this looks somewhat familiar. Isn't that what I showed you a lot with that aluminum ring that kept floating? I didn't have it on its side, but I had the ring that was floating here. And so if you pass current through the solenoid, which I will call now the primary, so if I pass current through here, that's going to make a flux go through the aluminum ring. That change in flux would result in a EMF. That EMF would result in a current. That current then would result in the ring being a magnet, and that magnet, together with the fact that this is also a magnet with current in, would end up repelling each other, and that was our discussion there. I don't think they want you to go too far and calculate the force of repulsion, but I do think they ask for the magnetic field. Let me keep reading. It says, assume that the axial component of the field produced by the solenoid is about half as strong over the area in the end of the solenoid at the center of the solenoid. Okay, also assume the solenoid produces a negligible field outside of its cross-sectional area. So remember we talked about an ideal solenoid, that the field is uniform, that it is all on the inside and nothing on the outside. And they say go ahead and just assume there's nothing on the outside. It says the current in the solenoid is increasing at a rate of 270 amps per second. A, what is the induced current in the ring? At the center of the ring, what is the magnetic field? And then C, what is the direction of the field produced by this induced current in the ring? Well, let me start with the current. What is the current? And so there is Faraday's law, because I will get a change in flux. And so the current would be the EMF divided by the resistance. The EMF is from Faraday's law. And so putting the new stuff, Faraday's law, together with the old stuff, Ohm's law, that should produce our current. Notice I've dropped the negative sign. I'm not going to worry too much about the direction here for the current yet. That was part of question C, what direction is it? So at this point, let me just calculate the current, how much current is in that ring. All right, well, as I start to fill in some numbers, I think this was 3 times 10 to the minus 4, if I recall right. So there's the resistance in that aluminum ring. N is the number of turns. Ooh, how many is that? It said like 1,000 or something like that? 1,000 per meter? So is N 1,000? What's N? 1. Why 1? Why not 1,000? Yeah, remember, this part of the equation is calculated. What is the EMF in the, what we might call the secondary? What is the EMF in the second coil? The second set of windings. In other words, what is it in the aluminum ring? And there's only one loop to that aluminum ring. So that's the N that I want. I want to know how many are in the ring. And so don't confuse our N's. Don't get me wrong, that 1,000 is going to be important, because that 1,000 is then connected to how strong is the field produced by that solenoid. So that is coming, but that's not the N, and I want to make sure we don't mix those two. All right, so now as we can continue on here, I can then do my flux, my dot product here, and have something that looks like this. So I've got a 1 over 3 times 10 to the minus 4 for the first term. Then I've got the derivative of. Well, one thing nice about the solenoid is the solenoid has a uniform field, roughly, at least in the ideal case. They did talk something about it. They said, you know what? This solenoid is not an ideal solenoid. I don't know if you caught that in the reading, but if you go back 2 chapters, when we derived the equation for the magnetic field in a solenoid, that's what we had, right? But that was an infinitely long solenoid. It probably would make most sense to put the ring at the center of this solenoid if you wanted the flux to be as close to this ideal case as possible. They don't. In fact, they give us a little clue here. They say that the flux from this solenoid probably tapers out at an angle, something like this. And so, as you put a ring around it at the end here, this aluminum ring, the magnetic field is not going to be straight in line with the area, is it? Fortunately, they gave us a way to handle it indirectly. I mean, read it carefully here. Here's what they say. They say, assume that the axial component of the field produced by the solenoid is half as strong over the area of the end of the solenoid as it is at the center of the solenoid. So what they really mean here is this field is probably best labeled at the center of the solenoid, this infinitely long ideal case. We don't have that. We can get close to it if we put it at the center, but we're not at the center. We've moved to the edge. So what they're really trying to say then is there's some kind of angle here. And so they're giving you a shortcut way of saying the flux would be something like this. It would be 1/2 of what you would expect in an ideal case at its center. And so I'm going to go ahead and then put in my 1/2 and also put in my mu naught n and I and then my area. Okay? And so that was the key part of that phrase, to make you realize that, okay, there's the ideal case, and then there's the more realistic case at the edge. And so without proof, they say that. By the way, when you take this class again as upper division, you will, that's a common proof to go through that shows that the axial component is about 1/2. So they just tell us, so I'm going to use that. But now let's look closely at the rest of my numbers. There's a derivative here. Any of this change with time? Yeah, the only thing that is changing with time is the current. And so the EMF that is produced because of the changing current. So of all the combinations we can have for a changing flux, either by changing angle or by changing area or blah, 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 this is the simplest one, or maybe I shouldn't say simplest, but a special case where it only changes because the current changes. And that's actually kind of my lead-in into the next chapter. The next chapter you're going to see, we're going to jump back to electronics. Electronics then will have currents that increase and decreases as switches are opened and closed or as you plug them into AC. So a common example of using Faraday's law is where what changes the flux is the current instead of a generator where it's spinning. Many of you have already looked ahead or in the circuits. We call this fancy case the induction of the circuitry, but that is what we have here. We have an inductor. We have a case where an EMF is being produced because of the change in current. Okay? And so that's my change. Now I guess I should be careful here because I just noticed I do have a change in current, but wait a minute, I thought this side equaled current. Okay, good. So maybe I should put a little subscript P for primary and subscript S for secondary, if that helps you. I know it often helps me because I've got a bunch of things going on here. I really have two coils, right? Two coils with, you know, two ends, two eyes, two magnetic fields, and I need to keep it straight. Which coil am I working with here? And so if this one causes the change in that one, then it makes sense to call this the primary and this one the secondary. Okay? And so we are looking at the change in the primary. So the rest of these numbers I think you know. I'll put the 2 together with the 3 over here and make it a 6 times 10 to the minus 4 there. The mu naught is the 4 pi times 10 to the minus 7, so I'll put that in. Here's n. What was little n again? Okay, good. The turn density, the number of turns per meter. And this is in the primary. And so they did say that that was something like 1,000, if I recall. Yeah, there is 1,000 turns per meter. Now, it doesn't look like it's even a whole meter long by those dimensions. So I doubt if there's 1,000 turns, but if it was a whole meter long, it would be 1,000 turns per meter. So there's the I I'm leaving here. Oh, here's a good one, area. What's that one? Yeah, must be a circle, pi r squared. But again, I have two circles up here. So which circle is it? Yeah, it's the little one, or the primary one. Now, I know it's supposed to be the flux that goes through the secondary. So you're tempted at that point to say it's the area of the secondary. But what do we know about the flux produced by this primary? Yeah, none outside of its core. And so the only flux we get is the stuff that is in its core. And so that's why I would put it as the 3 centimeters, 0.03, and square that. And now I think I know all the numbers, and maybe I'll even put this number in. They said calculate the EMF at the moment that the current is changing by 270 amps per second. And so that should be the current. So let's see what I get here. In the top I have a 4 times a pi times 1 times 10 to the negative 7 times 1,000 times, it looks like another pi, times a 0.03 squared times a 270 divided by 6 times 10 to the negative 4. So it looks like after all of this I come up with 1.60 amps. And so there is the current in that ring up at the top. And so there is and really the main thing I want to show you, but B can be just as interesting. It takes us back a chapter. It says then, all right, what is then the magnetic field at the center of this secondary? Well, that sounds familiar. How do you calculate the magnetic field from a single ring? A mu naught, an I, an R squared, a 2, X squared, R squared to the 3/2 power. Does that look familiar at all? All right, and so that's what we learned when we did Biop's of Art, where we took a ring and we went along its axis, a distance x from the center, and calculated it. Unfortunately, this one reduces down a little bit, because if you set x equal to 0 here, this breaks down to even an easier piece. This goes away. This r squared cancels with the square root, and then the 3 cancels with one of those, and you get that for the magnetic field right at the center. And I think that's what they said. Let me come back here and read it. Yeah, what? At the center of the ring, what is the magnitude of the field? And now if I put my numbers in here, this is 4 pi times 10 to the minus 7 for mu naught. My current is the 1.6 amps. That's what I just calculated there. My radius here is which one? Yeah, it's the 5 centimeters, right? And so 0.05 for the distance there. So again, getting out my calculator, 4 times pi times 1 times 10 to the negative 7 in the numerator. 1.6, divide that by 2, divide that by 0.05, and it looks like we're at 2 times 10 to the minus 5 Tesla. And so that's the field that is produced by that secondary. Okay. So again, I think one of the challenging things for this chapter and for the ones coming up here is keeping track of the primary, the secondary. They each have an N, they each have an I, they each have a magnetic field. Okay. And so keeping track of which R and which A and which N and which I can can be a little challenging at first. Now back to this last part, C, what direction is the current, is our Lenz's law. And so here we have Lenz's law to help tell us the direction. And so remember, it says this, that the direction of the current in the secondary is such that it will oppose the change in flux, which is coming from the primary.
You have an R squared first part, and there's about an R in the bottom, with an R still along with it.
You're not talking here, you're talking here?
Yeah, that's a little different. Start the first equation.
So from here to here?
Yes.
So this is an R squared. And then this part here would take a square root away. Then I'd have R cubed.
Oh, okay, I see.
And then, yeah. Maybe too sloppy. I got a, maybe that's a better pen. A little cleaner. All right. And again, now Lenz's law is going to say we oppose it. So they deliberately put in the picture the direction of the current going into the primary. So I can say, okay, now let's increase the current. Now, actually, they don't say where it's increasing or decreasing, or do they? They could be more clear here. They said the current in the, oh, they do, good. The current in the solenoid is increasing at a rate of 270 amps. Increasing. So they're saying at this moment that the current is already going in this direction. So let's take a look at the flux already going in there. All right, well again, that's why we got to go back a chapter here or two and say, look, I'm going to take my right hand, and if I curl my fingers in the same direction as the current, so it looks like the current is curling over the top and out in front, which would tell me my thumb is pointing this way. So right now, this solenoid, the primary, is producing flux going this way, right? And of course, if you increase that current, that's going to make even more flux go this way. So the increase is that way. So we want to get a flux or a current such that the flux goes that way. So I'm going to take my right hand again and think now about the secondary. I'm going to point my thumb that way. I want to oppose it. And so my fingers would curl around that way. And so that would be the direction of the current in the secondary, at least at that moment in time, and because things could be changing. But nonetheless, there would be the direction of my current. Fair enough? Too simple? Go to the next chapter? More examples? Yeah. Ready? Shall we try this one? All right. Same basic idea, except now we're going to jump with the toroid. And so I grabbed the toroid again. You might recall this one from when we did the toroid. This toroid and that one there looks like it has a little rectangular cross-section to it. But we know from previous chapters that the toroid produces a pretty strong field. So what happens if you wrapped a secondary, and they show the secondary in brown. And so here, this kind of blue-green is what I'll call the primary, and then the brown I will call the secondary. Well, you might have even recognized it on this one when I passed it around. Now this toroid does not have a rectangular cross-section, but what it does have is a secondary. It's got some green wires wrapped around the main primary wires that are in red. And so as I change the current in my primary, I will the flux through the secondary. That will induce a voltage in my secondary. And so there is the Faraday's law. Watch, let's read this together. Here's number 18. It says, a toroid having a rectangular cross-section of A equaling 2 and B equaling 3 and an inner radius of 4 consists of 500 turns of wire and carries a sinusoidal current given by the equation I equals a maximum current sine omega t, where the maximum current is 50 amps and where the frequency is 60 hertz. A coil consisting of 20 turns and colored brown in the figure is linked with the toroid as shown. Determine the EMF induced in this brown coil as a function of time. So again, what's the EMF? How much voltage is produced in your secondary? All right, well, let's try it again. I'll clean this off and start again here. They don't ask us to go quite as far as that first problem. That first problem we had to get voltage, and from voltage we had to get current, and from current we had to get magnetic field. But this one asks for the voltage in that secondary. So, number 18, the EMF, the voltage. And I'm just going to put magnitude. Well, I'll leave the negative in there, why not? Negative N times the rate of change of the magnetic flux. Okay. And so I'm trying to find the EMF. Now again, EMF where? Well, in the secondary, in the brown one. So maybe the first question to ask is that N up there. Number of turns. Is it a 20 or is it a 50? 500, excuse me. It's the 20, right? That's the number of turns in the secondary. So I will put negative 20. Then I will take the derivative of the flux that goes through the secondary. All right. Well, why don't we start here and ask ourselves a couple of questions. B. Is B a constant? So can I pull it all the way out here? It's really two questions. Is B a constant with space? Is B a constant with time? Well, maybe we should go back a chapter here. What was the equation we learned for the magnetic field produced from a toroid? Isn't the magnetic field coming from the toroid? Yeah, so it was mu naught times N times I over 2 pi R. And so one of the things we learned about the toroid is the field changed. It was great. It made a nice strong field, but it wasn't a constant value. That was what's nice about the solenoid. With the toroid, you didn't have a constant value. On the inner part of the radius, which in this cross section here, there would be a stronger field, and as you moved out, it would get weaker and weaker and weaker. So maybe that answers the question I just asked. Is B a constant? Nope. Can't pull B out in front of that integral. And of course, B is determined by the current. And this said that the current in this toroid is 50 amps times sine omega t, where the frequency is 60 hertz. So they say the frequency then is the omega over 2 pi. So they go sine omega over 2 pi of, well, maybe I'll just write it as 2 pi times 60t. And so maybe we should talk about this equation, but they have said that the current does change. So again, I ask this question. Is the magnetic field a constant? No, it's not a constant in time. It's not even a constant in space. So don't try to pull it out of any of these. There's no way that can come out. How about the angle? That is a constant, right? The alignment of the field from the toroid and the coils in the secondary, that doesn't change. Doesn't change with space and doesn't change with time. In fact, what is that angle? It's 0, right? Here and down. I wonder if they're trying to say it's 0. I mean, we could have done something fancy with it. Oh, I don't know if I should call it 0 or play their little game, but if you angle it a little bit, then the area would be slightly bigger than this area. But by the time you took area times the cosine, you get that. So maybe I'll just leave those together here and say, look, this together is that area. And then we don't really have to specify what the angle is. But I'm not real sure that that's really what the author is after here, that the cosine of the angle, as you tilt it, the area you integrate is bigger, but of course then it's bigger by a cosine function, but then you're multiplying it by a cosine function. So you're going to get the same thing here. So I'm going to put then a mu naught, an n, an I, a 2 pi r. That is the magnetic field. Okay. And so there is the magnetic field from the toroid. So the little bit of area, maybe I'll think of this as being in strips. So I'll take one strip plus another strip plus another strip. So my area would be the length A times the thickness of a strip, which I will call dr. So this is an A and this is a dr. I guess again we could argue that it would be dr over cosine theta times cosine theta from up here if we didn't exactly align it. But again, I don't think that's what he's after. Let's just say they're perfectly aligned here, and we'll cancel those off because these are going to be cosine of 0. Pardon me?
What did you mean again? dA times the cosine of theta? Why did you combine them with
Yeah, this is the part that, like I said, I don't think he really wanted us to get into. But let's say this is... need a good picture here. This is the cross-sectional area of the toroid. Fair enough? And if your loop here is not parallel with that, if your loop here is angled a little bit, okay, then the area where there is flux is actually bigger than this. So if I had a line here that was a distance of b, and I crossed that line at some angle, then isn't this a little bit longer than b? Right? I'll call it c. But if this is the angle between them, isn't the cosine of CB over C, right? Or put another way, the length C is B divided by cosine of theta. So the length that I'm going to integrate is actually a little longer than B by a factor of cosine theta. So that's why the author doesn't really have to say whether or not that loop is angled there or not. It's going to be the same flux as if it wasn't angled. Now that kind of makes sense if you think the mental picture, flux is the number of lines. So if you got a number of lines and then you twist it, don't you still get the same number of lines? And you can see that in the math that the cosines will cancel out there. Okay. And in fact, maybe that's how I should have done it instead of gotten into the geometry and just said, look, it may or may not be an angle of 0, but it would be the same flux as if it was an angle of 0, so let's calculate it that way. Then worry about what the angle is. And again, that's why the author doesn't have to specify what the angle is. All right, so what do we have so far here? All right, so far, we've got the 20 in front here for the number of turns from the secondary. We've got a time derivative and an integral, and this is the magnetic field from the toroid. This is the area from the toroid. Anything that is a constant. Well, why don't we go through this? What's n here? Okay, is this the 500 or the 20? Yeah, that's the 500. And I'll pull it all the way in front because the number of turns is not going to change over space, and it's not changing over time. It's not like more turns are developing or losing there. So I'll just pull it out in front. Also, it's kind of nice that if I messed up these two ends, I'd still get it right. Okay, so they're just kind of multiplied there. All right, so that's good. Mu naught. In fact, I'll group the mu naught with the 2 pi. That's just another set of constants, so that's 2 times 10 to the negative 7 when I pull that one out in front. Current. Ooh. Well, here's what they said about the current. The current in the toroid changes with time. It's 50 amps and then goes plus minus, plus minus, plus minus. So it's sinusoidal one. So what am I going to do with that one? Right, so I will pull it in front of the integral, but not in front of the time derivative. And so I need to take that derivative still, the derivative of the current as a function of time. A, well, that's that height of the toroid, if you will. They don't show it in the diagram, but he had it here. He said the A was 2 centimeters. So it was 2 centimeters high. So I'll take the A, 0.02, and pull it out in front, not only in front of the integral, but also in front of the derivative. And it looks like what I'm left with is dr over r. Obviously, the r does change as I integrate out, finding the flux that is in my toroid.
So doesn't the toroid or the secondary loop act as an inductor? I mean, it's a coil, so it...
Yeah.
So how could the current be constant over space? Because as it reached the beginning of it, as that pulse first hit, it wouldn't hit the other side immediately.
Oh, no, you're mixing inductors. When you have a circuitry, okay, whether it has an inductor or anything else, the current in the series is the same everywhere in the circuit. It's not like you get more current at the beginning and then less later on. What an inductor does is stop the current from generating right away with time, but not with space. But the current throughout this, I mean, the current throughout this whole toroid is the same. Now, I think what you're getting at is that current may not be the same as I would hope it to be, because I go to change it, then I get a back EMF, and so that affects my current. But the current is the same all the way through. No. Okay, now in this case then, the limits of my integral are from the inner radius, which I think they said was 0.04, until you get to the outer radius, which would be 0.07. So 0.04 to 0.07. And so inner radius of 4, going out the distance of B, and B was 3 centimeters. All right, so this finally gets me to the end of the problem, which is to say, okay, so the EMF in my secondary is, I wonder if I should put these together, because 5 and a 2, that's a 10, and then 3 zeros. So I'll just put the 10,000 together. So there's the 10,000. Oh, maybe I should put it together with, well, I'll leave it alone for now. 2 times 10 to the minus 7. That'd be another easy one. Another easy one, I guess, would be the 0.02. But the big one I want you to see is right here, is that the derivative of the current then would be 50 amps. Derivative of sine is cosine 2 pi 60 multiplied by time, and then 2 pi 60. All right, so there's the omega, like we saw when we did the generator a half hour ago or so. Okay, and so there's the derivative of the current. And then I've got this integral to do, which is a natural log, and it looks like I got 0.07 over 0.04. And so now I have some numbers that I can put in and get the EMF. So 10,000, 1, 2, 3, times 2 times 10 to the negative 7 times 0.02 times 2 times pi times 60 times 50 times the natural log 7 over 4 and then the cosine function, but I'll leave that alone. And so that's 0.422 cosine 2 pi 60 t. So there's the EMF. So there's an EMF, and of course it changes with time, which is to be expected since the primary, the current, changes with time, and the secondary is the voltage induced because of that. Try 53 then. 53's got a nice little subtlety in the mathematics that's neat to see. In fact, it makes a really nice, what's called a ballistic galvanometer. We've used galvanometers. What is, you may remember the galvanometers we used? What was the galvanometer measuring? Remember, it would deflect one way or the other when we... Yeah, and it was current, so it was kind of like an ammeter, but it was just a needle that moved one way or the other. It wasn't really calibrated, and of course you calibrated it could be an ammeter or it could be a voltmeter depending on how you set it up here. But this is often referred to as a ballistic galvanometer because it will measure how much charge flows, not how much current. Watch this one. It's number 53. And it's kind of a clever idea of asking not really what the current is and not really what the EMF is, but more of what is the total charge that flows through your circuitry. Watch here. It says, a plane of a square loop of wire with edges of A equaling 20 centimeters is perpendicular to the Earth's magnetic field at a point where the Earth's field is 15 microteslas as shown in the figure. The total resistance in the loop and the wires connecting it to the ammeter is 1/2 ohm. If the loop is suddenly collapsed by horizontal forces, pulling as shown, what is the total charge that flows through the ammeter? Well, first of all, let's just stop with the basic physics. Would this, by pulling this square, would this produce any current? Yeah, isn't there a change in the flux? I mean, if there is a field going in that square, and you take the corners until it goes flat, so it looks something like this when you start, and something like this when you're done, haven't you changed the amount of flux? Not because you changed the angle, and not because you changed the strength of the field, but because you changed the area. According to Faraday's law, then, that should produce an EMF. that EMF should be negative, the number of turns times the rate at which the flux is changing. Well, in the first case, I'm going to have just a single loop. So this little square up there is made out of just one loop. So I'll put n equal to 1. That's probably the easiest part of it. Then the flux, being the first calculation, would be something along the lines of, well, the B field doesn't change with space or with time. The angle, maybe I should have left myself some room here, doesn't change with either space or time. And so I just have an integral of the area, which reduces down to the rate at which the area is changing. Now, they don't say anything about this pole. Is it a uniform pole, meaning it moves out with the same force, or is it, and therefore we get an acceleration? And so the actual movement of this wire can get pretty complicated. So therefore the EMF and the current can get pretty complicated. But fortunately, I don't really need to know all of that, because they're not asking for the current at any given instant. They're asking for the total charge that flows through. So let's take Faraday's law written here and say, well, the current then is going to be the EMF divided by the resistance. So this would be a minus B over R times the rate at which the area is changing. So again, the amount of current depends on how quickly is the area changing. And how quickly the area is changing depends where you are on this, well, it's starting, it looks like a little square or a diamond, and then it's getting flatter and flatter and flatter. And so the rate of change is very complicated. I probably could write something out in terms of geometry, but again, we don't need to, because the current is dq dt. So if you want to know how much current is flowing, integrate the current as a function of time. And so if you integrate the current over time, you get, depending on your plus minus definition, but you get an integral of the area. That is then the change in area. Yay! So that's why actually solving the EMF at any given point, or the current at any given point, would be a pretty complicated problem. You have to know how the area is changing. And so you have to know how the square is being pulled. Fortunately, we don't need to know any of that, because we do know the total change in area. This B field is 15 microteslas. The resistance is a half a ohm. And the change in area is from, well, the whole area of what it started with. And so it started with A squared, A by A, which they said A was 20 centimeters, so 0.2 meters there. And so that will give us, and I suppose we could even put a negative change in area so that we get a negative that cancels off. And then we'll call it a positive charge, or we, you know, that's a matter of definition of which way the current's flowing, positive and negative there. So again, the minus sign's not a big deal, but the value, the magnitude is. So 15 micro times 0.2 squared divided by 0.5 comes out to be 1.2 times 10 to the minus 6 coulombs. And so about a microcoulomb of charge flows through there. And this doesn't really show it, but ballistic pendulums do that. They're called ballistic because they're usually put on a little gimbal in a magnetic field. So as it flows through there, it deflects. And its deflection depends on how much charge flows through there. So it's a good way of measuring how much charge can flow. So we have devices that measure current, ammeters, and we have devices that measure total charge that flows through there. And they use Ampere's law here to, not Ampere's law, Faraday's law to get there. '30's next on my list. You guys are kind of quiet. Is that good or bad? Burned out? Ready for some rest? Probably are. Not that you're going to get any over this break. This is the time to catch up. You're going to... Tell mom and dad and grandpa that you'll be there for the turkey, but you got to go right away back to your room and study, study, study. Right? And you got to travel up north. Take the train so you can study, 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 study. All right. Well, 30 is a Lenz's law. We did one earlier with Lenz's law, but I grabbed this one thinking, okay, let's not forget this, because a lot of times, and particularly these last ones, I just calculate the EMF. Sometimes I blow off the negative, sometimes I don't, sometimes I justify it, sometimes I don't. But the reason for it is I kind of like to keep it separate in my mind. One is A, what's the magnitude? The other one is B, what's the direction? And so let's do this one. Here they say that you have a loop. You've got a rectangle, you've got a resistor, you're going to move a magnet south side pointing towards the loop, and you push the south side into the loop. First part of the question is, will that produce any current? Yes, why?
Change in flux.
Faraday's law, right? There's going to be a change in flux. And so as that magnet gets closer, there's a change in flux. That produces an EMF. And so that little loop is kind of like a little battery, if you will. All right, so thinking of that loop as a little battery, which way does that little battery point? Which way does the current flow? Will the current flow from B to A or A to B? All right, well, imagine the little magnet far away. You would say there's no flux going through your loop. So as the magnet gets closer and closer and closer and closer, it is putting more flux. What direction? Well, the south is where the fields point into. So if I'm using my thumb for the flux, I would say that magnet is making more flux go through that way. Fair enough? So Lenz's law says the current or the EMF is produced to oppose that. So if we're getting more and more that way from the primary, then the secondary is creating a current this way. So B to A. There's the direction of the current. It's B to A, and as we kind of push our little magnet in there. Let's try this one. Yeah.
Sorry, can you explain how magnetic fields go through the loop?
All right, so let this be my loop. Let this be the south side of the magnet. Okay? If I just look at the magnet, mentally picture lines going this way, right? Into the South Pole. So there's a bunch of lines here. All right, so if I've got the loop over here and the magnet far away, there is no flux in there. As I get closer and closer and closer and closer and closer, there is getting more and more flux lines in here, but they're pointing this way.
Don't they also have to travel out of the north and towards the south?
Oh yeah, so as I'm getting closer, so if I were to draw these flux lines, so here is my south, here is my north. They look something like this, pointing this way. So if my ring is right there, okay, and again, I'm only interested in the ones that go through my ring, right? The EMF is produced by the change of flux in my ring. So when this magnet is far away, I would say there's none going through my ring. And as it gets closer and closer and closer and closer, these flux lines, which go around the outside of it, they don't go through the ring,
Okay, that's what I was getting.
are then penetrating through that way.
So how do you know at what point that you're close enough so that they don't go through the ring and then back the other way through the ring?
Oh, no. I would always have, let me draw another picture here. If I was far away, okay, okay. I mean, yeah, really large. Okay. Granted, when it's really large or far away, right, there are going to be some flux lines, well, like those, which never even go through it. There's going to be some others that go through it one way and then back the other way. Okay, so those don't change. But there's always going to be the outer edge, like that. There's always going to be more in, coming back in and then going out. There's always a few out here. So when I'm really far away, since a lot of them either don't go through or they go in and out, the change in flux is only a small number. So far away from it, if I move it, I'm not going to get much of an EMF. So I'm going to get most of my EMF when I'm closer. But I will always get more pointing in. Okay. Let's try this one, 48. It's a magenta one. It's really not anything new in this chapter. In fact, it's all Faraday's law. I'm just sitting here myself kind of debating, all right, have you seen enough? Should I move forward? Or should you see some other of these? But I like this one because it puts together our circuitry of the past. Okay? Which, by the way, we've learned a lot of physics these last couple of chapters, which is why we're going to go back to circuits in a minute. Now we're going to start applying what we've learned to our circuit. So sort of like we did in the first half of class where we learned about electric fields, and that led to capacitors and resistors and batteries and our circuitry. Now we can add one more to this, which is then a magnetic effect, inductors. And so that's where we're about to head here. Well, thank you. All right. But look at this one here. This is the picture they give you for 48, and it says this. It says 2 infinitely long solenoids, which are shown only in their cross-section in the picture. So those green dots are the magnetic field from 2 solenoids. Okay? Pass through the circuit as shown in figure 48. The magnitude of B inside each is the same, and is increasing at a rate of 100 Tesla per second. What is the current in each resistor? Now, look carefully at this circuit. Do you see any batteries? Well, I guess directly the answer is no, but where is the EMF? Yeah, exactly. This is Faraday's law. There is an EMF here. The EMF is produced by the change in flux. So if I were to draw this maybe a little differently, I might have, let's see, what do they have? A 6, a 3, and a 5 ohm. So here's a 6. Here's a 3. And here is a 5 ohm resistor. Were there any others? No. Okay. And so here's my circuitry. But what I'm trying to claim here is this first loop right here has the equivalent of a battery. It has an EMF. Now I need to decide which way that EMF goes, but I'm going to just open up the top here and say there is some kind of EMF here. Let's use Lenz's law to get that direction. You can see that they have the x's, meaning the field is pointing in. And they said the field was increasing, if I'm not mistaken. The magnitude of the magnetic field inside each is the same and is increasing at a rate of 100 Tesla per second. Now, I'm going to take what they mean by increasing is the strength of it is increasing. So it's already pointing in. And that means it's getting bigger in. So then this, which I'll call the secondary, is where the induced EMF is. So if the field is getting stronger in, my right hand means I should point out, right? And then that should make an EMF or should make a current this way. At least by itself. There might be other batteries and other things going on. But by itself, this would have an EMF. So I am going to replace it with a battery, which I will call V1. There's EMF number 1. And likewise, I can say in the second loop, if all I had was the second loop where the magnetic field is coming out, as they say out, but they got the green dots pointing out, and if it is getting more and more out, so they're increasing, okay, I would want to oppose it. And so nature would create an EMF this way. And so that EMF could be listed like that, V2. Now, I think that looks more like the circuitry you're used to. I mean, could you, once we find voltage 1 and voltage 2, couldn't you find the current in each of those? And that's where we'll go here. Yeah.
Could you call it a current source instead and just say that that side's going to produce a certain amount of current?
Well, but Faraday's law tells me how much voltage it's going to produce.
Okay.
So I'm not sure I want to go down that road. But of course, there's also source transformation. So not to say it couldn't be done. But the fundamental physics part of it is Faraday's law produces an EMF. And then how much resistance you put in there determines how much current. So that's kind of the cause and effect. All right, so with the EMF then being my next step in my calculation, I can say, all right, Faraday's law is this. Let's do voltage number 1 now that we first got the direction of number 1. Then we can look at the magnitude of it. So let's not even look at the plus or minus there for a second. Let's also just throw away the n. Not that I throw it away, but it's equal to 1. We've got just one wire making one loop in our secondary. Okay. And so this then is the change in flux that goes through our loop. And so as we look at this, what's changing? Well, the flux is definitely changing. But the position that it is changing is in the solenoid. And we know a lot about solenoids. We know that the magnetic field in this case is going in. The area vector is in. And so this part is an angle of 0. The area then is probably worth talking about, or maybe I should say the magnetic field, because the magnetic field is a constant in space. Isn't that what we learned about solenoids? And so this solenoid makes a nice strong field the same everywhere inside of that solenoid. And so I'll just pull the B out in front and then have an integral of dA and get an A. But what I can't do is I can't pull the B in front of the time derivative, right? Because I said that's what is changing. The strength of the field over time is changing. But the area is not. So I'll pull the area in front and then have the derivative of the magnetic field. And that's the part that makes the problem fairly easy. They gave me that. They said it's 100 Tesla per second. So this is 100 Teslas per second. But let's look at area too. Don't miss this one. What's the area? So is it 0.5 squared because it's the area of this square? Or is it pi times 0.1 squared because it's the area of the solenoid? Yeah, it's a solenoid, right? Because that's where I'm getting the flux from. If there happened to be more flux in this area, then I would use that flux too, because the EMF is the change of all the flux within the whole square. But the thing is, a solenoid doesn't produce any flux outside of its core. So it would only make sense then to put a pi times 0.1 squared for the area. And so there is the voltage number 1. And how about voltage number 2? Yeah, same logic, right? There's going to be one turn. It's going to be still a solenoid, so the angle is going to be 0. It's going to be the area that can pull out, but it's the area only of the solenoid. Then it's going to be the field. And so we get a pi, what's the radius over here? 0.15 squared times 100 Tesla per second. So there's the V2. And so I have both V1 and V2. And it'll be okay, I'm just going to leave it there. I know the problem said go on and get the current, but again, we can write down our 2 equations, 2 unknowns, or 3 equations, 3 unknowns, if you want to set it with 3 currents, and put it into our matrix and solve it. So once we have that set up, and that's what I wanted you to see. Let's take the new stuff, let's apply it to the old stuff. Which is why I thought this would make a good last one. Let's try number 50 before I kind of introduce the next chapter here. And one more example. This one, also a magenta one. 50, 50, 50. Oh, that's 48. 48, 47. Look at this one. This one's going to take some past chapters, together with this chapter, together with introducing us to inductors in the next chapter, taking us actually all the way back to physics 121 too, because we got to do some mechanics here. All right, so you can see why it's a magenta. But here's what it's saying. It's saying build a little circuit. Oh, number 50. Number 50. And so I'll clear this off. And so number 50 says, take a close look at this setup. Now they start off with a battery. Okay, so here is a voltage. Okay. Then there is some metal rails, and they lay a metal bar across here. Well, what's going to happen when you put a metal bar across here? Aren't you going to get current? All right, so in my first picture, I will say, all right, so here's the battery. Here is a metal rail. And then I will play this metal bar across here. And I guess my first reaction is I should start to develop a current here. Okay. But once that current starts, what is it saying about the magnetic field? Now, and this takes us back a chapter. If you get current there, and so in this case, if the current is going down, then I would have, let's see if I get this right here, I'd have current down, magnetic field out. Wouldn't that put a force on the bar? And so this metal bar should be pushed in that direction. This is the railgun one we talked about a little bit. All right, so now we get this push. But let's add to this railgun. What else is going to happen? What are we learning in this chapter? As it is moving out, what's happening to the flux that is in this rectangular loop? It's increasing. And as that flux increases, what happens? It makes an induced EMF. This is Faraday's law. So, maybe the best way to describe this is like that last one. In addition to the EMF from this external battery, I have the equivalent of another battery, and that other battery is really the strength from Faraday's law. Let's use Lenz's law to get its direction first. So, as this metal bar is moving out this way, wouldn't that be more and more flux coming out? So, I would want to generate an EMF in such a way that the flux would go in. So, taking my right hand and pointing my thumb in, my fingers would curl around in this direction. And so, as this thing is trying to race out, it's really trying to oppose it by making a current go in the other direction. And shall I label this as the external? And this is the EMF. I'll call it F from Faraday's law. And that's probably a better way to look at this circuit. That there's really two EMF here. There's one from this external power supply, but in addition to that, there is the fact that this thing's trying to move. And if it's moving really fast, isn't that going to be a lot of change in flux? Isn't that going to be a lot of EMF? Yeah. And unfortunately, that's going to be the limiting factor. You probably could have guessed it was this way, because if you didn't have an EMF, this would just go faster and faster and faster. That would be great. If the EMF was the other way, that too would be weird, because then the two would be together, and the faster it went, the more current it produced, the faster it would go, and then the faster, and then fast. I mean, you would clearly have a violation of conservation of energy, so it wouldn't correlate with our physical world well either. So that alone says, okay, the EMF has to oppose the change in flux here. And this is really no different than what the one I passed around last time. Did I pass it around, the copper and the magnet? Did you guys watch it drop through? Yeah, and as you watch it drop through, that induced current in the copper tubing opposed its motion, slowed it down. It didn't make it go faster. Too bad. I mean, you know, and the faster it went, the more it produced, and the more it produced, the faster it went, and, you know, it would just go all the way down the tube and go faster and faster. But that's not the way it's going to work here. All right. Well, let's read the problem. Now that I kind of gave you the gist of the problem from the figure, here's what it says. It says, a bar of mass little m and of length d. So the bar has mass of little m. It has length d. I think those are in the picture, or at least d is in the picture. And resistance r slides without friction on a horizontal plane. So there's a little resistance in the bar. Okay, I'll put an R in the picture. Slides without friction on a horizontal plane. Moving on a parallel rails as shown in the figure. A battery that maintains a constant EMF, script E, is connected between the rails. And a constant magnetic field B is directed perpendicular to the plane of the page. Assuming that the bar starts at rest, what is the equation of the velocity of the bar? So as this thing gets pushed out, V as a function of time equals what? So you can see where the mechanics come in there. All right, so we've got our circuitry from past chapters. We got our force on a bar with a current and a magnetic field from past chapters. But we also got to put this chapter, which is the, what I'll call that secondary EMF, the Faraday's law here. And so let's work on that. Why don't we start with the part that is in this chapter? Let's start with Faraday's law. So the EMF, according to Faraday, is minus n times the time derivative of the change in flux. All right? Since I already did the direction, I'm going to ignore the negative sign. You good with that? Also, how many loops do I have in what I would call the secondary? Yeah, just one. So I'll throw that off to the side here. And so what I have is the time derivative of the change in flux. So let's calculate the flux. They do say it is a nice uniform magnetic field. They also say that the magnetic field is perpendicular to the plane out of the board. That means then that this just reduces to B times A. And if I take that even one step further, A, being the area of the loop, would be its width, which I'll call D, but it would also be its position, and there's nothing in that drawing yet, but let me call X the distance as measured from the constant EMF, so I'll call that an X. Because if you look at this, the only thing that's changing is the X, right? The magnetic field is a constant, the D is a constant, and you get this step, which is what we actually did last time in class. We called this a motion EMF. We said that the EMF produced by a magnetic bar is the magnetic field times the length of the bar times the velocity of the bar. I think we used L last time in class, but this time they have a D in the problem. Okay. So there is this chapter. That's what's new, is the EMF. But now if I use that to say what is the current in this circuit, I would say the current is the sum of all the EMFs divided by its resistance. That's Ohm's law. And so I have the external EMF minus the Faraday's EMF divided by the resistance. So I've got E minus VDV over R. And that would be the current in here.
So that EMF would be the external?
Yeah, so this little script one is supposed to be their little script one here. Yeah. Maybe I'll put the external like I did before to make it clear. So EXT, yeah. In other words, I just got two batteries and they're fighting each other. So the net voltage is, you subtract the two, all right. And then divide it by the resistance, Ohm's law. So that's the current. But then if I go on and say, all right, let's go back to force, which is current times L cross B, which I think was 2 chapters ago, something like that. But that would be the magnetic force once we get a current. So putting this into the puzzle here, I'll start off with just the direction of the current and the direction of the magnetic field. So as we look at this, in this bar, the current goes this way, the magnetic field is out, the angle between them is 90 degrees, and that means I just get an I, L, and a B. And so there's the magnitude of the magnetic force. And then the current is what I did earlier on. So let me put that in there. That's the external EMF minus BdV over R. So there's the current. Times the length of the bar. So back in chapter 29, we used L for length, but in this picture, we're using D for the length. So let me replace my L with a D. And then let me put a B. Can I put the B first? So that it's in the same order as that one? Because if I write it this way, someone's going to think that's a derivative, and I don't want you to think it's change in magnetic field. It's B times a D, okay? All right, so there is the force. Now if we go back to physics 121 and divide both sides by mass, we get acceleration, right? And then if we integrate acceleration with time, we get, yay, velocity. So there's what I'm after, right? What is the equation for the velocity? So to do that, I got to get acceleration. To do that, I got to get force. To do that, I got to get current. To do that, I got to get EMF. To get that, I got to do Faraday's law. And so those were the steps I went through here. So this then should be the integral of, maybe before I do the integral, I should do a separation of variables. It'll make it a lot easier before I try to do the integral. So let me pause here for a second and just write acceleration as dv dt. dv dt then is bd over m time, and I'm going to put the r out there, how's that? And then I've got the external minus bdv. Because, as you might recall, the best or easiest differential equation you can solve is the one that, fortunately, all of one variable is on one side and all of the other variable is on the other side. And so if you can ever have an equation like this, you thank your lucky stars and just say, yes, I can separate them, and then you just have to do an integral of each side and you're done with the problem. Unfortunately, not too many come out that way. Fortunately, all the ones in our class do, because we're not, you know, at a 220 level. Some of you guys are doing some pretty hard differential equations, but at this class, we give all the ones that are separable. And you can see that right here, that if I leave this as a dv and put the external field minus bdv here, and then the other side go bdmrdt. I've got everything with v's on one side and everything with t's on the other. Actually, there is no t's even. So once I then do the integral of this, I now have an equation that has v's and t's, and I have an equation for the velocity of this rod, and that was the point of the problem. What is the velocity of this rod? So on the left-hand side, I guess I get the natural log of ext minus bdv. Oh, chain rule. Minus bd, I believe. Is that right? Derivative would put it downstairs. Yeah, okay. And then the other side of the equation is going to be a bdmr t plus a constant of integration. Yeah.
Are you implying that r is constant over time?
Yeah.
But as the bar moves, you have more traffic.
Yeah, oh yeah, okay, but the way they worded it was the rails have no resistance, the bar has resistance. So all the resistance is in the bar. So as it moves further down the track, you don't change R. Yeah. Otherwise, now we have another piece of this. R does change with time. And we could probably do that. Let's just say it was linear with time. Then we would have to put resistance.
That wouldn't be possible either, because only two of the sides are changing length. So it'd be some plus.
Okay, so we'd have a linear. Okay, so we'd have a linear function here, and I'm not sure you would end up with something that's separable. It looks like it's solvable, maybe separable, but that's not what they said in the problem. They're trying to keep it simple and just say the rails are thick and big, and the resistance is all in the bar. Okay. And then so then the resistance is the same as it moves across. So as we go to solve this, I'll put the BD over here. So that's a B squared D squared over MR with a negative times the T. This is going to be some other constant. Could I call it constant 1 and constant 2? Maybe that'll make it more clear. But when I move this and multiply it out by the distributive property, it's just some other constant that I don't know what it is yet. I'll soon find it. But then this gives me the ln of the external minus b dv. In order to solve for v, I have to take the anti-log. So when I take the anti-log, I get e to the minus b squared d squared mrt. I guess technically I get e to some constant, but that's just some other constant, so maybe I'll just write it as constant number 3. I have yet to find out what that is, but I soon will. If I now rearrange this so it says external EMF minus C3e to the minus b squared d squared t over mr equals b dv. Finally, I can get an equation for v when I divide by the BD. Now I'm at a good spot to begin to ask myself, what is constant number 3? Probably best done by saying at time equals to 0, v has to come out to be 0. So for that to be true, putting in time equals to 0 and setting v equals to 0 means that C3 has to be equal to the external EMF. So there's my external EMF. Yeah? No, it's not a derivative. This is B, the strength of the field. This is D, the length of the bar. Oh, I'm sorry. Where here? This one? No, that wasn't, that I know. But I probably should have wrote it as V times D, but that wasn't a differential either. That was velocity here, and that was D, the size of the bar. Yeah. So, yeah, as you point out, I probably, well, now that I got to this line, I don't have to. But yeah, it's not a differential there. I know it kind of looks like it. Well, finally, that gives me the answer I want, which is the equation for the velocity. It is the external EMF over BD times 1 minus E to the negative B squared D squared T over MR. And I know it was a lot of math, even a lot of physics 121, but you guys are experts with that, so that didn't bother you at all. You like the problems that have torque on them in the test, I can tell. Right. Right. So there's our mechanics. But like I said, it's gotten 4 different chapters that we put together between Ohm's law and magnetic forces and Faraday's induction and Newton's second law here. And once we put all that together, we have an equation. And so you can kind of see what's happening once you finally get this part. You see that it does have a terminal speed in the sense that the speed goes up and up and up and up until it reaches a maximum speed. And it's at that maximum speed where it's really not getting any help anymore from the external EMF, because it's moving so quickly that the induced EMF is then equal to the external EMF, and we're just not getting any more current, which means we aren't getting any more push, and without friction it's just going to keep going at that same speed forever and never and never and ever. And so we unfortunately have, or fortunately do have, Faraday's law, depending on what you're looking at. And when it comes to launching something into space or building railguns, the Faraday's law is an unfortunate consequence, which gives me just enough time to tease you about chapter 32. We won't do any equations or anything real, hopefully complicated, but enough that you see the concept. And got a little experiment set up so we can watch it in play. Well, Yeah, we'll watch it in play, and then we'll watch it again when we come back, because I want to solve some numbers for you, and not today though, and actually then change some parameters on the experiment so you can see it. But chapter 32 is really asking this question. It's saying, now that you've learned a little more physics, what if you took an external EMF, a battery? And you can see it's a lot like this problem. Is you can't determine the current completely by the external battery. If there's things moving or things changing, can't that also have an EMF? And that EMF has to be added to the equation and has to be figured out what to do about the motion. In this case, motion. In this case, current. Because if I were to do something like this, and put a switch there, and if that's all I did and I closed the switch, and if it was before this chapter, and I said to you, what's the current in there? You would say, E over R, right? Got some resistance, got some voltage, and you would say, all right, the current, I guess, looks like this. That current is a function of time. Calling time equal to 0 when I close the switch, you would just say no current, no current, no current, no current, no current, close switch, current, 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 and it would be an EMF over R, right? It's not as easy to notice in that picture, although it is true in that picture. Maybe I'll add to that picture. What if instead of just having a nice little wire across here, I had a wire that wrapped around a solenoid? And I want to emphasize to you, even if I didn't have a solenoid wrapped around, wouldn't there still be some flux and some change in flux as we went from no current to current? And so the point of this chapter is to go back to our circuits. The good news about this chapter, maybe I should say it's more good news for me, it's going to be real easy to teach. There's no new lesson. There's no new physics here. I'm just going to apply Faraday's to that situation. And what I want you to see, just like in this railgun, is what would happen here is as the current was trying to flow through here. So in this picture, the current would go up and up and up and up. And so using my right hand, I would start to get flux from the current. The current from itself would create flux. And as it tried to make flux in here, this would make an EMF trying to make current go the other way. And so there would be a EMF from Faraday's law. Really what I'm trying to get you to see here in this beginning step here is I have been showing you things like this. Current goes through this one. It induces a flux in the second one. And so we've been calculating for the last 2 hours an EMF in the secondary based upon current and situations in the primary. Fair enough? But as the current changes in the primary, doesn't it have an effect back on itself? So forget the secondary. Well, I shouldn't say forget it, because I want you to keep remembering those too. But that's one class of problems. The problems we've been doing, and we will actually do later. But this chapter is called self-induction. You don't need the second coil. You can just have a single coil. And that's what I'm trying to illustrate here. A single coil by itself will then try to make current flowing through it. As the current tries to change, that will produce an EMF. And so I should write this as a change in the flux. Oh, time, yeah, thank you. Right? And that is what we're going to see in this chapter, that there is an EMF produced, a self-EMF, what we're going to call then for short an induction. And so if the EMF that is produced from this circuit produces an EMF on itself, we call that the induction of the circuitry. And so what would this look like? Instead of just being that, what would the current look like? And so current as a function of time would now be, well, I guess I would have my EMF minus N times the flux per time divided by the radius, right? And again, that's why I chose to do this one at the end. I thought it's a great lead-in into what we're about to do. That the change in flux within the circuit itself can affect itself. It doesn't just have to affect a secondary. And it can do that too, obviously. But it can also, in a very special and useful case, affect itself. And so, without crunching the numbers yet, we'll do that when we come back, we should probably see something more like this. What happens now, do you think, when you close the switch? Yeah, when you first close this switch, you're trying to go from no current to a lot of current. Isn't that a huge change in current? Which means you would produce a huge EMF, right? And I have yet to prove this to you, and I wish we had more time and I would, but we're going to see that the EMF that is produced at the when you first close the switch is just enough to equal the external one. So what voltage do you get at the top? 0. And so a moment later, you still have 0 current. But the current has to be increasing. Why? Well, in order to have a voltage, we have to have a change in flux. And so when you first close the switch, it's not as if the current will just ramp up to some top number here. It will start to go up there, yes, but it's going to take a little bit of time. And what's going to happen then is there will be an effect looking something like this. It will eventually get all the way up to the same current we had before, because at some point we will get a steady current, a steady constant current. Now if you have a steady constant current, how much EMF do you get from Faraday's law? Yeah, none. And at that point, this whole coil is just like a wire. And so the lesson here, or really more next time, is that when you first close the switch, you get a huge EMF. After a long time, after the switch has been closed, you get no EMF. In between, it's kind of fun to play with and watch what happens when it goes from here to here. But as a demonstration to show you this, I thought we'd finish and get started with the next chapter by hooking up the oscilloscope here and saying, look at this circuitry here. I'll start with a power supply at 10 volts, and this will be my switch. Okay, so there's that power supply, 10 volts, here's the switch. So when I hook it up, and maybe for clarity, let me disconnect my oscilloscope, but I am going to hook this up and run it through a solenoid. Where's that little one? I ran over here. I suppose I could use this one here. But if I run it from here to my, grab this wire. So this will be my, I guess this will be my switch right here. Okay, so I will connect it here, and it'll run through my solenoid, from my solenoid to my resistor, and from my resistor back. And in the meantime, so let me put my switch over there. This then will be the voltage that I pick up with my oscilloscope. Okay? Now it only happens right when I make connection. So I have the oscilloscope in a mode that you may not have seen before. I'll start with this comment that it's 5 volts per division, but if you look up there it says stop mode. And basically what that means is it's not measuring anything right now. It's in stop mode. If I activate it, it'll take a measurement. So what I did is I said, okay, take one quick measurement. And so it did. And so what it did is it measured the voltage. 0, 0, 0, 0, 0, 0, 0, 0. Nothing real exciting. I don't have anything really connected yet. But if I get it ready, you can see it's saying trigger. And what it means by that, it's waiting for a trigger. It's like it's listening. It's kind of monitoring what's going on, but it's not displaying anything. It's waiting for something to happen. When something happens, then I will display it. And in my case, my trigger is time-wise is here, level-wise is here. If I ever get a voltage of 5 volts, it'll display it. So let's see what happens. Let's take the switch and see, when I hook it together, the voltage. And so what I have is, and the time is pretty short, I mean it's 250 nanoseconds per division. And so we got nothing, 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 nothing. Then something happened. And it ramped up the current, as I said. It will not just shoot up dramatically like this. It'll kind of arch over. How much does it arch over? Well, doesn't that kind of depend on how much EMF you're getting from here? And doesn't that depend on how many turns you have? So one more and then we'll go here. What if I leave that one on the screen? So let me save that one. Save it. And I'll leave it on the screen. Let me reset. Oh, I still got the switch on, so that's why I'm getting 10 volts. Okay, let me undo my switch. And let me change something up here. Why don't I change the number of turns that it goes through? I'll just go through a smaller number of turns. It says here this is 40% of what it was there. So I should have a different number of turns. I hope that's enough to actually see it. But let's see it again. And see how much quicker it built up to its full charge. Because I have less effect from Faraday's law. I have less effect from what we'll call induction. Well, that's my teaser, and so we'll do more on Tuesday. Have a good Thanksgiving. Stay safe. Drive carefully. Oh, that's more.